Welcome all. Now we are going to discuss the theorem 11.1 bounded inverse theorem. The statement is let x and y be Banach spaces and let f element of BL of xy be bijective, then f inverse is an element of BL of yx. Okay, that is if x and y are Banach spaces and let f element of BL of xy be bijective, means f is a bounded linear map from x to y, be bijective, then the inverse map f inverse is an element of BL of yx. That is, f inverse is again a bounded linear map from y to x. Okay, we will see the proof. It is very simple. Let x and y be Banach spaces and we have f element of BL of xy is bijective. That is, f is a map from x to y is a bijective bounded linear map. Okay, then clearly f inverse from y to x is linear. The proof is in the brackets. Suppose f from x to y is a bijective linear map, then f inverse is clearly from y to x and is defined by f inverse of f of x is equal to x. Now if we check f inverse of c into f of x1 plus f of x2, we can see that this is equal to c into f inverse of f of x1 plus f inverse of f of x2, means f inverse is a linear map from y to x. Okay, now f element of BL of xy means it is continuous, and since every continuous map is closed, we can say that f is closed. If f is closed, then the inverse map is f inverse is also closed. Okay, the proof is in the brackets. Suppose f from x to y is a closed map and is bijective. We have to show that f inverse from y to x is a closed map. For that, choose a sequence yn such that yn converges to y in y and f inverse of yn converges to x in x. We have to show that f inverse is closed. For that, it is enough to show that x is equal to f inverse of y. Okay, we have the sequence yn element of y, means since f is on 2, there exists xn element of capital X such that f of xn equal to yn for every n. That means f inverse of yn is equal to xn for every n. Okay, then we have chosen yn such that yn converges to y and f inverse of yn converges to x in x. So f inverse of yn converges to x in x means xn converges to x in x, and yn converges to y in y means f of xn converges to y in y. Okay, that is, we have xn converges to x in x and f of xn converges to y in y, implies y is equal to f of x. Since the map f is closed, we get y is equal to f of x. This means x is equal to f inverse of y. Okay, so we have proved that if yn is a sequence such that yn converges to y in y and f inverse of yn converges to x in x, then x is equal to f inverse of y, means that f inverse is a closed map. So we have proven that the map f inverse from y to x is a closed linear map, and we have x and y are Banach spaces here. So by closed graph theorem, we can see that f inverse is a continuous map. That means f inverse is an element of BL of yx. Okay, this is the proof of bounded inverse theorem. Now we will see an example for bounded inverse theorem may not hold for maps on non-complete normed spaces. For that, let x equal to c naught naught with norm 1 and y equal to c naught naught with norm infinity. Then clearly x and y are not Banach spaces. Consider the map f from x to y defined by f of x equal to x for every x element of x. Then clearly f is a bijective, linear and continuous map. Okay, that means f is an element of BL of xy and bijective also. Now consider the inverse map f inverse from y to x defined by f inverse of x is equal to x for every x element of y. Then norm 1 of f inverse of x is equal to norm 1 of x, because f inverse of x is equal to x. Okay, now for the sequence xn equal to 1 1 1 etc 1 0 0 0 element of c naught naught, where the ones occurs in the first n places, we can see that norm 1 of xn is equal to n and norm infinity of xn equal to 1 for every n, right? Then norm 1 of f inverse of xn is equal to norm 1 of xn, which is equal to n, which tends to infinity as n tends to infinity. Means that f inverse is not bounded for the sequences xn. Okay, so from this we can infer that there is no constant alpha greater than 0 such that norm 1 of f inverse of x is less than or equal to alpha into norm infinity of x for every x element of C naught naught. This means that f inverse is not bounded and so it is not continuous. That means f inverse is not an element of BL of Ix. Okay, this is happened because here x and y are not Banach spaces. That is, here x and y are non-complete spaces, non-complete normed spaces. That's why we have found a bijective bounded linear map, but its inverse is not an element of BL of Ix. Okay, thank you.